So, some little information about frequency modulation. Have you studied anything about the frequency modulation in the bachelor course?
Yes.
So you have basically know what is this modulation index and all this kind of stuff.
I believe that they will do something with high frequency, low frequency for the modulation, things like that. Right? They will vary the frequency over the time.
So it, yes, in this case, the idea, maybe I will not go with very deep theory around this, but this is a kind of analog modulation which is still used around because this is quite efficient, and maybe it's not efficient, but it is very robust modulation, and it allows high quality audio broadcasting. Yes, and this is because the contents of FM signal do not get affected by some analog filtering. Yes, and if you put some analog filters, they do not affect the spectrum of the transmitted analog signal. And this is very big benefit because in case of, for example, amplitude modulation, if you start filtering of the signal, the spectrum will be heavily affected by all filters in the transmitter, receiver, and as a result, usually this high frequency content of the audio is heavily damaged, and that's why you cannot even dream about any high quality audio, but FM allows it to do. And this was realized very long time ago. This was realized in 30s, yes, it was some guy in United States. His name was Edwin Howard Armstrong. Yes, it's very, let's say, lot of Armstrongs familiar, some famous Armstrongs in the United States, and this is another Armstrong, and he was engineer who developed this, and he had started a business even dealing with all this FM broadcasting. But in 30s, there was a very big depression in the United States and a lot of crime, and finally some corporation had bribed, I think, some lawyers, and as a final, they somehow managed to steal all patents from this guy. Yes, and finally he was poor and ended his life in the suicide because of all these problems. Yes, because it was quite wild times. And this is some company called Radio Corporation of America, RCA. This is quite familiar. It was quite big company, but it lost his position in the market with development of the television. Yes, and because they didn't recognize that color television could be some great future, and that's why they lost. Now, even I think it doesn't exist, but it was a huge company at those times. It was dealing with radio broadcasting mostly, yes, some kind of they started with AM broadcasting, and later did this FM broadcasting. Okay. So here is some formulas. This is how it is described, that in fact, what you are modulating this part, yes, when you are changing phase of the signal, in fact, yes, because amplitude is constant and carrier frequency is constant, yes, but this modulation index gets multiplied by by some modulating signal. In this case, this is a cosinus, yes, but this signal must be derived before the transmission. That's why, no, not derived, it must be integrated. That's why here is a sinus, because you integrate your information signal. That's how you get phase from the frequency, because frequency is derivative of the phase. That's how you, if you integrate, you get back phase from the frequency. So normally you, in the transmitter side, you need to integrate your audio signal. But for audio, of course, this is integration. It is like low pass filtering, and you doesn't, okay, you have some phase changes in the components, and some maybe high spectrum components get suppressed a little bit, but this is not big deal. And then even if you do not do this, their integration, this audio will be still decodable by the receiver. And here is a picture how it is done. Yes, this is a carrier frequency which get added to the integrated information signal. And here you also, this multiplier usually is controlling this gain, or this is, in fact, this affects this how wide is the spectrum of the FM signal, and here you can affect by this modulation index the spectrum, and later you integrate and multiply by add this carrier frequency as a constant, and then later put this as a phase. Okay, this is not constant, this is some linear growing term which gets added to this, and then you feed this into the cosinus, and so on. If it is digitally implemented, this is somehow similar to this voltage controlled oscillator or numerically controlled oscillator in the PLLs. Yes, it's very, very similar by the design. And this is two kinds of FM really exist. We have narrowband frequency modulation, and this case modulation index is much more smaller than 1. And in this case, you have very, very simple spectrum consisting from 3 components. And spectrum, this, if you look to magnitude spectrum, it looks very, very similar to amplitude modulation signal. And this narrowband FM has advantage that it has a bandwidth which is very small, and it is used mostly for data communication, because in this narrowband case, this if modulating signal has broader spectrum than this deviation of this narrowband, then spectrum becomes dependent from the frequency content, and you will receive the same problem as in amplitude modulation, where you have problem with high frequency components. And in broadband FM or wideband FM, you have very wide spectrum. So for example, in this broadcasting, where you can, for example, still hear the radio station, we will use lab work, the deviation is 75 kilohertz. So that means the total spectrum is about 150 kilohertz. And whereas the audio is just 20 kilohertz. That means the bandwidth of the radio station is much, it's like 10 times higher than this audio. But at this if you use relatively high carrier frequencies, this is not a big deal, because at higher frequencies you can afford such bigger chunks of frequencies. That's why FM is not used on the some short or middle or long waves. Yes, because you cannot afford 200 kilohertz devote to these FM stations. Okay, this is what, and here is some formulas that if you have narrowband FM, you can have 3 components. It looks like amplitude modulation and wideband FM. This is, for example, commercial, which is used for the commercial radio stations. This is deviation, and the total bandwidth is 200 kilohertz. Yes, so you can remember that radio stations come after 200 kilohertz. So, for example, you have 100 megahertz, then next is 100 and dot 2, 100.4, and so on and so on. And then step is 200 kilohertz. And this is because also the signal is a stereo. Here we have modern radio stations are transmitting stereo signal, and also some RDS. This is for radio data system, which is transmitting some data like radio station name, some, I don't know, I remember that sometimes it show currency, rates, and so on and so on. Some very small text information could be displayed. So maybe it's some from this lecture, from the bachelor course, that if you wish to calculate the spectrum of the FM signal, you can use Bessel functions. And in this case, your frequency components are proportional to the appropriate Bessel function. So this is carrier frequency is a 0th Bessel function of first kind. This is the first Bessel function of the first kind. This is the second Bessel function of the first kind, and so on. Each Bessel function, which is dependent from the modulation index. Yes. You should sample these Bessel functions appropriately to the modulation index, and you will get the values of those frequency components. And they are gradually decaying always, and that's good thing that depending from the modulation index, you have faster or slower decaying those spectrum components. And that's how, using this modulation index, you can control the bandwidth of the FM signal. In fact, you control the bandwidth using the deviation, but this deviation affects the modulation index efficiently, and that's why those Bessel functions are not dependent from the deviation, but they are dependent from the modulation index of the FM radio station. And this modulation index in turn depends from the deviation and the frequency of the modulating signal. So if you are modulating using some kind of, let's say, here is not formula. Okay, maybe I will write, but okay, maybe it's not that necessary to write you, but just you have to remember those terms: modulation index, because it must be put somewhere in the model. Deviation, maybe. Okay, let's draw something, because it could be more interesting, not that boring that I just showing the slides and talking something. Which is not maybe that interesting. Okay, I will try to give you some hints. And this will be recorded. And in case if I travel to Germany, still, then you can look to it and maybe use it if it's necessary, especially the second part when I will especially concentrate on doing this lab work. So, so frequency modulated signal usually.
Also, you are not sharing the screen.
Not sharing, yes, it's showing that I'm sharing, but what you see now?
Just you.
Yes. Very interesting. And now it's video, yes, what you see?
It's only video.
But have you seen sharing before?
No, I was just looking at my computer.
Okay, but in the computer it was sharing, yes?
No. I opened the slide from Portus.
Okay. Wow. This is total junk. But how? Maybe, but because it's projector working like this, it shows some. Because it shows that I'm sharing the screen.
Maybe I can do it in the computer.
Let's check what it. Maybe it has two screens, for example, and one screen is maybe it shows on this second monitor or something like this.
No, it's in computer also. It's just only the video, not shared content.
Okay, I will try.
Yes, now it's okay. It's because he didn't switch to the share content.
Okay, it was in Zoom.
Yes.
But hopefully in the recording everything will be fine then.
Oh, I don't know.
Because it will record, I think, because I'm the host, but this computer which is not host, it is just some random room 426 account. That's why it's interesting that it's 426 but not 428. Yes, but it's really funny, but okay, that's not a big deal. And okay, now you see on the big screen this what I'm showing. Yes.
Yes, I can see.
Okay, so I'm sorry, it was not intentional. That's why I was just thinking why you are not looking even to my side. Yes, but I now understand. So, okay, let's go back. So the idea, in fact, is very simple, yes, in the FM, that you have some carrier. And for example, you have some modulating signal. Yes, for example, this is your sound. This is the time. So in fact, that means that you are moving your carrier back and forth, yes, like this, and that's how you created your signal. The resulting signal is some kind of same amplitude but different frequency signal. Yes, this is the time. But if you wish to describe this, that turns out, and okay, maybe put some terms here, that this distance on one side is called deviation. This is a delta. I think in lecture slides it's called delta F. Yes. And this deviation, by the way, is somewhat, it's a maximum offset, but with the, of course, for example, in reality, this is the offset at 1 volt. That means that your modulating signal here is 1 volt. So if your signal, which you are controlling this, is bigger than 1 volt, then your spectrum could become, not spectrum, but this wave could go for the bigger offset than the deviation. So the deviation, this is offset at 1 volt controlling signal. This is important to remember, because if you start modulating with too big signal, for example, 10 volts here, then your signal will be 10 times wider than the deviation. And this must be taken to the account. This is deviation, of course, goes to both sides. Yes, this is again, so the total, if the signal is symmetric, the total is 2 delta F. So for example, in case of commercial transmissions, this delta F is 75 kilohertz. So this is approximately 150 kilohertz. And luckily that if you have, this is a linear modulation, so you can decompose your controlling signal into some sinusoids. Yes. Yes, for example, you can decompose into harmonics. And let's imagine that there is some harmonic of this signal, only one of many, yes? And in this case, you can describe your FM signal with some Bessel functions. Yes, that here you can have some they are approximately occupy the bandwidth equal to deviation, but in fact they are go beyond, yes, and depending from the situation they must go quite in theory they are infinitely wide, and you have components very, very far away from even far away beyond this deviation. So this is some kind of side effect, yes, because for example, let's imagine the deviation is here, yes. This is because you have transitions in this modulating wave, and they call these components outside the deviation. But they are not big, and normally you can think about this deviation as this bounding area of this. And now if you know the frequency of this, let's say call it omega information, yes? Okay, let's call it frequency information, because okay, if it has frequency information, then you can derive this modulation index. It's beta, yes? Okay, it's beta, usually beta. And this is this relationship between this deviation and frequency of information signal. So larger is the no, it's opposite. So larger is deviation, larger is modulation index. But if your modulating signal has larger frequency, it will lead to smaller modulation indexes. And that's how that's why the spectrum, in fact, is not very much dependent. The bandwidth of the total spectrum doesn't depend on the actual frequency of this modulating signal. So if you decompose it to many harmonics, each harmonic will produce approximately same bandwidth set of Bessel functions. And this is very good because that means that if you filter this signal with some filter and cut those, for example, away, you will not affect one certain frequencies in your audio spectrum, but you will affect them all. And that's why your sound will be still okay without any distortions. It maybe will have some noise because you have reduced some components, but will not change this pitch of the sound or some. And this is very, very important for high quality audio transmission. And this modulation index, that's why when you calculate the spectrum, you are mostly dealing with this modulation index here. And this is very important factor, yes, and it's worth maybe after all worth to remember that this is just relationship between deviation and frequency of this controlling signal. Of course, if the controlling signal is some kind of complicated, some audio with many harmonics, then you have different modulation index for each harmonic. You cannot say modulation index for some non-sinusoidal signal. Yes, it is different for each frequency. Okay, this is very info signal. And if you are transmitting real audio, you have many modulation indexes. For each frequency, it is different. But finally, the spectrum of, and we will see in the lab work, it will look like pile, yes. And it is quite well limited to some, I don't know, usually this is approximately deviation, but in fact it could go up to 2 deviations, yes, depending from the, okay, maybe if you look strictly, maybe okay, maybe I will draw it more precisely. And we will look it also, and this is also pictured in the logarithmic scale. So FM radio station is looking like this. So, and here you have this carrier frequency, and this is this deviation. So you still have quite a lot of components outside this deviation range. So normally they fade away after another deviation here. And that means that the commercial radio stations actually are a little bit overlapping with each other, but here is approximately, I don't know if it is much like minus 30 or I don't know, even like maybe 50 dB. So it is, those elements are much more smaller. And we will look to this in the lab work. Okay. I will go back to the lecture slides, maybe. So this is about the demodulation, yes. In fact, there is very simple method, use differentiation. Then this is complex delay line discriminator, which we will use in our lab work. And this is really simple device, irrespective to this very complex notation, but this is very simple device consisting from 3 very simple blocks, and it works very well. And the phase lock loop also could be used for the demodulation of M signals, and those modern state-of-the-art FM demodulation chips are employing this technique because it allows highest lowest signal to noise ratio to achieve high quality demodulation. Using differentiation, you just differentiate your signal. You see, if you differentiate FM signal, there is some formulas doing derivative, but actually what you look here, then this is your information signal modulated by sinus. So then if you just later on go with amplitude envelope demodulator, yes, it's a tag detector. This is automatic translation, but this is envelope detector. Yes, it's like from amplitude modulation. You go via the diode or some rectifier and you could get audio. So actually what means that you derive your signal and then go through the envelope detector. But actually this is, I think, quite risky, because I think if you have, there was some issue with okay, theoretically it's fine. It has some DC offset and this is your information signal. And theoretically it will be fine. This KFM, this is modulation index. This is somewhat, sometimes it's in lecture slides called K, but sometimes it's called beta. Okay, this is the demodulation shown. Maybe it's not very relevant picture, because here you do not have anything special. You just have this standard processing using software-defined radio. And after that, you have this so-called baseband signal. And here you have baseband modulated IQ signal. That means that it has in-phase and quadrature components. After that, you go to the MATLAB or GNU radio and demodulate. So this is a derivative-based demodulator, which could be assembled or in Simulink or GNU radio. Some students tried to build this and it worked. So this is a differentiator, but because you have quadrature signal with I and Q components, that means it has a real part, an imaginary part. You could not ignore one of them, because if you ignore one of them, you will get huge loss in signal to noise ratio, I believe. That's why they process both using differentiate both, then sum the results. And also this is a weighting element which adjusts this amplitude of the signal. Of this demodulated output, because what you do is you just square both then add, so it is like energy detector, which, and you divide by this energy, this demodulated output. That's how it becomes independent from the amplitudes. Otherwise, this will produce quite, I think, different result depending of this amplitude of incoming FM signal. But this shouldn't be like this, because amplitude in frequency demodulation doesn't play any role. And what we will do in our lab work, we will assemble this guy. This is super simple device. You see, it has some delay line, then phase shifter, and then we will just, but phase shifter is just, we will use some derivative, and we will multiply here, and then take phase of this derivative, this multiplication, and here we will get demodulated FM signal, and it will have very good quality, and even you will see both stereo channels, and even you will be able to notice RDS channel, because if you look to some lecture slides, maybe here you can see this is the contents of commercial radio stations. Yes, and commercial radio stations are not, if it would be just a simple FM, they should show the contents of the radio station should be just like this. Yes. After FM demodulation, you must have this audio spectrum from 0 to 15. And that's why if you have some kind of old-fashioned FM receiver, like produced maybe in 60s or 70s, when the stereo was not used, and also maybe because if you have super cheap some receiver, I don't know, some 1 cent chip, or I don't know, but nowadays all I think FM demodulator chips, even cheapest one, have full stereo decoder inside, because some extra 100 of the transistors doesn't make very big difference in the production of microchips. But nowadays, if you demodulate, and we will see also this in our lab work, the spectrum consists from this mono channel, which is sum between left and right stereo channels, some pilot, which is just some carrier transmitted at 19 kilohertz, and then there is a so-called, this is amplitude modulated using 38 kilohertz, but this is not standard. This is a so-called suppressed carrier amplitude modulation. That's why you do not have carrier here. And here you have lower and upper sideband, which are exactly the same, because this is amplitude modulated suppressed carrier. This is AM DSB SC, so-called dual sideband suppressed carrier. And here we have also on the 57 kilohertz, also using same kind of modulation with DSB suppressed carrier. You have some data channel, very, very low speed, like, I don't know, some 10 bits per second. RDS, so-called radio data system, which is transmitting some text. And if you have appropriate tools, you can decode this text and also show this on the screen. And I think even books, some people have demonstrating this using MATLAB or something. You can build this also. It's not very complex, because it is, I think internally, this is like ASK or amplitude shift keying or something, like very simple data modulation. And then how we get left and right channel, we just subtract this from this. And after subtraction, depending of what you subtract from what, you will get either left or right channel. Because if you subtract from left side, this right side, L plus R minus L minus R, you will get L minus L and R plus R. So you will recover right channel. And if you subtract from the right side, the left side, you will get left channel. Because if you L minus R minus L plus R, that means R gets erased and L will be twice. No, opposite, yes. In this case, it will be minus 2R, yes. If you L minus R minus brackets L plus R, L will be delete each other, but R will be doubled. So it will be in the electronics, in the stereo detector, you have just two subtractors, which are subtracting in two different ways, those two analog signals, because most of the analog demodulators are analog. They are not using any DSPs, so it is kind of just transistors which are, or op-amps which are subtracting two analog signals to get this stereo. And it gets very good quality. You know, the stereo receivers in, for example, they are not used a lot at homes, but in the car or, I don't know, on the move, on the headphones, for example, still people use this FM and the quality is excellent. It's not, of course, studio quality, like if you download it from the internet, but it's completely enjoyable. And finally, maybe some words worth to know that in United States and Europe, we have different standards for the FM broadcasting. And the difference is in this so-called preamp phases filter. And that means that in order to suppress some noises, this is somewhat similar to Dolby system. The transmitter is preamp phasing high frequencies in the audio spectrum. And then receiver will this blue one is a receiver de-emphasis filter, this frequency response. And you see, if you have this red combined with this right blue, everything gets correct. But if you use this red and this blue, you have different frequencies, because in the United States, this preamp phases start at one frequency, but in Europe, it starts at a little bit different frequency. And as a result, you have these green lines. If you use radio, which is produced in Europe, and if you take it to the United States, your audio spectrum will be slightly high pass filtered, yes? You will have like high pitch sounds in phase. And if you use radio which produced in United States, in the Europe, you will have like bass booster, yes? It will boost the basses, and it will be incorrect behavior anyway, because it will not produce correct decoding of the audio signals. That's why many modern receivers have this option when you come and say which Europe or United States standard you are using. For example, my car receiver, especially this, has this option. You can come and select where you are in Europe or United States, and it changes this DM phases filter, so they match the radio station preamp phases filter.
So what about mobile phones? Will the radio in the mobile phone works in US?
I think it also should choose, or maybe it detects automatically, because if your phone has GPS, maybe it will ask the GPS location and it will calculate, will find some location. Okay, if it has internet, I think it has a way to detect this.
It's not based on hardware. It's mainly some software.
But it's filtering. It's audio spectrum filtering. Yes, it's not just like you need to adjust some things into this analog processing chain in the receiver to have correct decoding. And for maybe mobile phone has no such high quality FM receiver. Maybe it's okay, because it's not very big difference. It's like you see, it's 4 dBs. It's tiny difference. It's barely noticeable. Yes, maybe for big musician it will be noticeable, but if you have the rest of high quality, of course, if you have the rest not that good quality, that you will not be able to notice this difference. And I never know about this. I just found this when I have started studying this frequency modulation, and I found, oh yes, indeed. And then I look to my radio, yes, and you have this option.